I2C, short for Inter-Integrated Circuit, has been around for more than 45 years and is widely used for intercontroller data communication. Even now, it's one of the most popular ways on how to connect microcontrollers to peripheral devices. The main advantage of using I2C is that you can have up to 128 devices connected to just one data bus with only 2 data wires. Those 2 wires are SCL, which is the serial clock line, and SDA, which is the serial data wire that is used bidirectionally, meaning it's used to transmit and receive data. Where the serial clock line is used to carry the clock signal from the host device to all connected peripheral devices. The data wire carries the data from and to all connected devices on the bus. I2C is a synchronous serial data communication protocol that is widely used for attaching low-speed peripheral devices to microcontrollers and processors in short-distance communications. As both wires are open drain outputs, pull-down resistors are required. When a device pulls the data or clock wire low, the resistors let the bus return to its normally high state. Without pull-up resistors, the I2C bus would float and communication would be unreliable. Note that some microcontrollers like the ESP32 have internal pull-up resistors, thus not needing external ones. However, it's still best practice to add external pull-ups. The next important aspect of I2C communication is how devices are identified and selected on the shared bus. Since many devices can be connected to the same bus, this system relies on a structured addressing method to ensure that the data is delivered correctly. Most I2C systems use a 7-bit addressing system, which allows up to 128 addresses. Although some are reserved for special purposes. In applications where we need more addressing space, I2C also allows 10-bit addressing, although that's not really used and not very common. I2C also defines several standardized clock speeds, which determine how fast data is transferred over that bus. Standard mode being at 100 kilobit per second, fast mode with 400 kilobit per second, fast mode plus with a whopping 1 megabit per second, high speed mode with 3.4 megabit per second, and ultra fast mode with 5 megabit per second. Most older microcontrollers only support the standard and fast modes, so 100 and 400 kilobit per second. Newer microcontrollers such as the RP2350 or the ATtiny 1660 also add support for the fast mode plus with 1 megabit per second. What should also be mentioned here is that those named speeds are only the clock speeds, and the actual data rate is going to be a bit slower than that due to protocol overheads, which includes the target address as well as acknowledgement bits. This directly brings us to the next point, which is the protocol. Every I2C communication begins with a start condition, where the master device pulls the serial data line low while keeping the serial clock line high to initiate the beginning of a data transfer. This is followed by the slave's device's 7 or 10-bit address. This is the device we want to send data to or get data from. After that, a read-write bit follows, where a 0 indicates a write and a 1 indicates a read. This bit is used for the device, the slave, to know whether to send or receive data. Next comes the acknowledgement/not acknowledgement bit, which is the bit our peripheral device, the slave device, sets to say that it has received the data correctly or not received the data. This is followed by the actual data we want to send or receive, which is cut up in 8-bit chunks, which always are followed by a acknowledgement or not acknowledgement bit. Finally, the communication ends with a stop condition, where the master releases both SCL and SDA lines, so they both rise to their nominally high level again. This signals the end of the data transfer and indicates that a new communication can begin. Now that we know how I2C works, here I have prepared a simple demonstration with an Arduino Uno and a 16x2 character LCD that uses I2C to display data. Actually, I haven't. Turns out that demonstration was way too complex, so here's a simpler demonstration. We're simply using an EEPROM instead of our 16x2 character LCD that's connected to our Arduino with I2C. The first thing we need to get is the I2C address of our EEPROM. Simply go to File, Examples, I2C, and open the I2C scan example. Now upload it and open the serial monitor. Here we can see that the EEPROM's address is 0x50 for the first block in this EEPROM. Now we need to open the EEPROM example and change the I2C address and upload it. Let's hook up an oscilloscope to our SCL and SDA lines to see how the signals look like. On the top, the yellow trace is the data wire, and on the bottom in blue is the clock signal. In the very beginning, even before any data is sent, we can see that our bus is at its idle state with SCL and SDA being at 5 volt. Next comes the start bit, which is this section right here, with SDA low and SCL still being high. After the start bit, the next 7 bit are our EEPROM's address, which is 0x50, followed by the read-write bit. This bit is low, meaning we are sending data to the EEPROM. Next comes the acknowledgement bit, which is also low, meaning the device has received our data. After that, we set register 00 to a value of 42, with our EEPROMs acknowledging both of those changes. And finally, communication stops with both SCL and SDA returning to their normally high state. In conclusion, we can say that I2C is a versatile communication protocol that's relatively easy to use with many devices. While transfer speeds aren't particularly fast, it's more than sufficient for applications like measuring temperature or other environmental data, and displaying it on simple monochrome displays. I hope you all learned something new today. Thank you all for watching. If you want to see more informative videos like this, make sure to subscribe. Bye!